Kia ora, Year 13 and Year 12. I'm finally going to start recording the Level 3 stats papers from last year. I'm going to start with the probability distributions one. So I'm aiming to do a part of one question per video, and they're going to be reasonably slow. I'm going to show the assessment schedule at the end, but in the first part of the video, I'm just going to talk through my answers. So this first question was about the Poisson distribution, and it was reasonably straightforward. The harder part of question one came in part B. So in this one, we're starting off with a basic Poisson question, right? And we know that it's Poisson because we're told that the mean number of emails per hour received by one email account is 1.3. So the giveaway that it's a Poisson is that I've got a number of things per unit of time, right? So a Poisson is one where we've got a discrete random variable, so that takes on counting values, per continuous something, right? So per continuous unit. So often that will be per unit of time, but you know from some of our sillier examples that it could be the number of ferrets found per hectare of farmland or something like that. The point here is that you can't have half an email, right? So your email values are going to be none, 1, 2, and so on. So using an appropriate probability distribution model, calculate an estimate for the probability that we get either 0 or 1 email during any hour. So we always have to watch that this time period in my problem matches the one that I'm told about. And in the first question it does. So we're going to use lambda is equal to 1.3. And what we have to find is the probability that x is equal to 0 or 1. So we can go straight to our graphics calculator if we've got one of those, and we're looking for the cumulative distribution. So PCD with lambda equals 1.3, and the upper number is 1, right? So that gives me probably that x is less than or equal to 1. And when we chuck that number in our calculator, we get out 0.6268. So if you're watching this and you're in my A-level class and you're sitting level 3, then you'll probably do this directly with the formula, and the formula will give you the same thing. So we have probably that x is equal to 0 or 1, and that's going to equal e to the negative 1.3 plus e to the negative 1.3 times 1.3. So if you're sitting there with a graphics calculator wondering when will I ever use this formula, well, you might use it in some harder problems. So the formula that I'm working with there is this one, e to the negative lambda times lambda to the x over x factorial. You don't have to memorize that. It's given to you on the formula sheet, but you're going to need to know how to manipulate it. But for this question here, all you've got to do is chuck it into your calculator and get your answer, and don't round it too hard. So go to 4 decimal places, 0.6268, and that's an achieved question. So let's look at the next part of the question, which is quite similar, except we're told to calculate an estimate for the probability that this email account receives at least 2 emails, but it's during a 3-hour period, so from 8 to 11 a.m. So what do I have to do with this? Well, this is a question where I have to fix the time period up and the lambda so that they match each other. And you can see up here, lambda was per hour, but here we've got per 3 hours. So we need to adjust that 1.3 to match 3 hours, and then we're finding the probability of at least 2. So we want the probability that x is greater than or equal to 2, but we want it with lambda is equal to 1.3 times 3, which is 3.9. And our graphics calculator and even our formula can't work with the top end of a Poisson distribution, because in theory we could go on forever. So we're looking for all of the emails, all of the probability that 2 or more emails come in, at least 2, but we find that by going 1 minus the probability that we get 0 or 1. So on the calculator, it's going to again be PCD with lambda of 3.9 and 1. So we get this number, and that works out to be 0.099185. So 1 minus the probability that x is less than or equal to 1 is equal to 1 minus this. So don't round too hard. and we get 0.9008. Right? If you're using the formula, you do it the same way that I did it to start with. So the third part of the question is the part where you have to really think about the model that we're using and whether it makes sense. And if you're sitting level 3 stats, you know that that's just as important as all the numerical stuff, all the calculated stuff. So we have to talk about one of the assumptions that might be invalid and discuss why this is the case. So I'm first going to just jot down the 3 main assumptions that you want to be looking at for when something, the conditions that we need for something to be well modeled with a Poisson distribution. So we need the thing to happen randomly. We need the things that happen to be independent of each other. And we need whatever the thing is that's happening to be happening at a constant rate. There's another condition that sometimes gets talked about, which is that things can't happen simultaneously. But this is usually a stupid assumption to focus on, and here's why. I want you to imagine here that you said, oh, emails can't arrive at exactly the same time, but in actual fact they do. Well, if you think about your inbox, it depends very much on how accurately we measure time, right? So we can always measure time more accurately so that 2 things don't happen at once, so that 2 emails don't ping into your inbox at exactly the same time. So the marking schedule said here, don't talk about that one, and I agree with that. I think it's a really weak assumption, but I think that these 3 can quite easily be criticised for a Poisson model. But the Poisson models, it's not a terrible thing to do. It's still a good place to start, right? So we're not saying we shouldn't bother to model with a Poisson. We're just saying it's not a perfect model. So here are the kind of things that you should say, and as usual, it should always be in context. The first thing is to say, well, do emails really come into your inbox randomly or not? And so this one and this one are kind of the same thing. Do emails come into your inbox at a constant rate? Well, they don't really. So let's think about why the rate of email arrival isn't constant. And we're always thinking in context. So what are things that might affect when email appears? Well, the first and most obvious thing is, I don't know about you, but I get more emails during the day than in the middle of the night, except for like overseas mailing lists and stuff like that. So time of day, and then be specific. More come in during working hours, especially if you're a teacher, right? So that's the first one, is the rate of arrival is not constant. Time of year was not constant over the time of year either. I think this is probably a better one to pick on though. But the time of year, when do you get more emails? Well, I get lots of emails around Christmas time from both retailers, so mailing lists that you're on trying to sell you stuff, and also from friends sending annual updates and stuff like that, right? So time of day, time of year, probably people get more emails, or older people who work have more emails during weekdays than weekends. So any of those, I think, would be a good answer to why the assumption that we've got a constant rate per hour is not that good, okay? So that's a good thing to talk about. Are emails coming in? Where are my list of things? Here. The other one to talk about is, are emails coming in independent of each other? So I don't think this is as strong an assumption to pick on for this question. But you can say that emails aren't independent, right? So emails don't arrive independently. Generally, if you send lots of emails, you're more likely to get lots of emails because people reply to other emails. Or one of the things that's in the marking schedule that I'm about to show you is that people send group emails, and then there'll be replies to all of those. But in general, the more you send, the more you get back. So let's now have a wee look at the mark schedule and see what was in here. Not surprisingly, it's exactly what I've gone through. So the first question was an achieved question, right, and 0.6268, so that was fine. The second one, this is one where it's a combined merit and excellence, and you have to get both the mathsy part of the question, but you can't get excellence without talking about the model assumptions really well. And that's because we're trying to get through this idea of true probability and theoretical probability. So in real life, email arriving is not going to be modeled by a Poisson distribution, but it's still a pretty good starting point. So you can see that the invalid assumptions in here, they said really specifically, don't talk about that emails could arrive at the same time. Okay, so they've talked about independence, constant rate, and emails arriving randomly. And to get excellence, you had to talk about one invalid assumption discussed in context for A3, and then it's really hard to see the difference between these two, right? I think you just had to do this in context thing really well to get excellence, and you had to get the number right. So big things on Poisson that you should have by now is that lambda must be for the right time period. And if that skill of looking for that and changing your lambda to match isn't getting really fluent, then the best place to go and do some practice on that is probably Education Perfect, or use the Walker book, or use the lovely Jake Will's website, the Maths NZ one. And let me know if you need any more questions on those. I'm going to do question 1B tomorrow, and then I'll see if anyone's watching them and decide if I'm going to keep going. Thanks for watching.